Hi, my name is Carlos Dominguez. I'm a product owner at the Intel Graphics Performance Analyzers team, or Intel GPA. And today we're going to be talking about game performance profiling. But more specifically, I'm going to try to take a stab at some methods that we can either employ ourselves or bring back to our team to hopefully lower the barrier of entry to finding and mitigating performance issues. This with the goal of making it more approachable to developers that may not be necessarily familiar or are intimidated by the process of profiling. And hopefully this will be performance profiling, or at least performance awareness earlier into the development process, not only by performance engineers, but also by everyone else involved in the team, so including artists, game designers, etc. This by showing them how to use the tools in ways that are not necessarily overwhelming, and leaving all of the heavy lifting to the tools. So we're going to be starting our journey with an introduction, just setting the tone of the conversation by not only talking about the importance of game profiling, but also scaling graphics performance to work efficiently in a wide range of hardware. Then we're going to give a little overview of the different tools that we're going to be using. And then I'm going to be presenting a profiling workflow, and I'm going to be going through it step by step with a deeper explanation and what data we can infer from it, and what next steps we can accomplish. And once we get in our journey into the point where we manage to find the bottlenecks and root causing them appropriately, what I'm going to be doing is like providing a little, what I've been calling a recipe of like a common bottleneck that we may see, and something that we can bring back to our team that without having knowledge of the underlying hardware, they could say, okay, if you see this, then it's probably because of this, this, or that, and this is how you can validate it, and this is how you can fix it. And I believe these kind of recipes can really help us like bring this performance awareness to our team. And then we're going to wrap it around and just bring it back to the introduction of scaling graphics performance effectively with a case study of optimizing the Unity's 3D game kit. For whoever's not familiar with the Unity 3D game kit, it's a demo that you can get in the asset store, and it already has like a few levels and like menus and stuff, and they already have 3 built-in quality settings. So we're going to be talking about how we managed to achieve to bridge the gap between the performance mode, which is what you see on the left side, and the fantastic mode that you see on the right side. So let's begin our journey with our semi-fictional, although quite real scenario where we may be developing a game in a high-end system. The game looks gorgeous, and it has all the bells and whistles that you would expect from a modern rendering engine. It runs comfortably at 30 FPS. And then somewhere along the line, the game is tested on a mainstream system, and reality hits. This can happen for many reasons, right? Like we may be trying to define our minimum or recommended specs, or maybe it was a requirement since the beginning for a target demographic, but we may have thought that the game was not ready to be profiled yet. And really, this could happen at any time in the development cycle. Unfortunately, more often than not, this tends to happen towards the end of the development cycle. And really, at this point, it doesn't really matter the reason. What matters is that the game is just not performing, and it needs to be scaled accordingly. And assuming that this was done later on, what matters is that most of the content is going to be created at this point, so modifying any of these assets will be very costly or prohibitive. So when the performance engineer comes along, then he or she likely did not create nor maintain any of these assets, and it seems like all that you can do is just start stripping out some of these effects, render passes, and whatnot. And while doing that, you may or may not achieve your goal, which is running at 30 FPS. But what you'll surely accomplish is that you'll degrade the visual quality, because all you're doing is just stripping down things, right? And since you're only stripping down things, it's worth also pointing out that nothing really changed in the high-end system. It's just still running the same. So here's where GPA comes in. And I'm not saying that this is necessarily magic or anything. What I'm hoping that I'll convey today is that not only like having tools that can give you the data that you need, but also like categorize it in a way that is understandable and actionable is essential. And also that while you're developing and scaling your graphics to a lower-end system, there's this symbiotic relationship so that some of the optimizations that you do in the mainstream hardware, it will actually reflect, and we're going to see that in the case study, in the high end, and then vice versa. So for example, in this case, and it can be pretty common, maybe we just stripped down a lot of things originally and we degraded the visual quality, but maybe the game was just like completely sampler bound because we just had all of the textures being 4K by 4K. And if we had actually spotted that accordingly, we could have mitigated it a little better by just addressing the issue by its root. So what exactly is GPA? So GPA is a suite of graphics performance tools created by Intel for the purposes of optimizing games and real-time applications. We are going to be looking at the tools individually, but we're not going to focus on a lot of the features. I don't want to overwhelm. I want to keep the conversation on message. We're just going to use the features that are going to help us advance this profiling workflow that I'm going to be defining. It is worth noting, though, that it works cross game engines and cross-platform, and then it supports all the major graphics APIs, DirectX 9 through 12, Vulkan, Metal, OpenGL. We also added some really cool features that we're really excited about, so we are going to be touching on a couple of those, but just as we need them. So without further ado, this is the profiling workflow that we're going to be focusing on today. It may seem obvious to a few of us, and depending on the level of expertise and the workload, the knowledge of the workload that you're working on, you may be able to skip some steps. But I thought it was really important to just set like the whole path so that someone that doesn't necessarily know how to approach performance profiling, they would have everything from step 0. It's also worth noting that there is an implicit loop back once you figure out some bottleneck and then you fixed it, and then suddenly either now you need to focus on another scene, or perhaps like the bottleneck is now not CPU bound, it's now GPU bound, or so on and so forth. So the first phase, as one may expect, it's just identifying what parts of the game we're going to want to focus our efforts on, which ones are going to give us our most return of investment. And this could be the scenes, levels, even just point of views. But also one thing that can be overlooked is like playing also with the graphic settings, just to see which one is the one that requires a little bit more love. And for this, we're going to be using the system analyzer. And once we determine the area in the game that we'll be focusing on, we're going to want to gain deeper insight so we can know where our next step should be. And for that, we need to know if we're CPU or GPU bound. And then for the CPU bound scenarios, we're going to be looking at some of the possibilities that we have for instrumentation and what kind of data we can get from it within the graphics trace analyzer, which is one of the tools in GPA. And in the case of the GPU bound scenarios, we're going to be looking at how can we quickly and without knowing a lot about the underlying hardware, how can we figure out what are the most expensive draw calls in our frames. And also with the automatic hotspot analysis, we can, with one click, figure out where in the graphics pipeline the bottleneck may be. So let's get started with identifying the scene. So for this, like I said, we're going to be using System Analyzer. So before we look into this step, I'm going to give a very brief overview of the System Analyzer tool. So System Analyzer, it's GPA's real-time performance tool. It collects real-time information across the system and helps you gain insight on like the impact of that the game's having on the system. It is also paired with some real-time overrides that you can see in the bottom left corner right there. And that can help you get like an initial assessment on where your bottleneck may be. But quite frankly, like usually like the bottlenecks may be pretty varied within our frame, so that will just give us an initial assessment. Then we're going to need deeper tools we're going to touch on later on to get a more definitive answer. Another cool feature is that it's actually paired with a HUD overlay that you can put in your game, which is particularly helpful when you're running in full screen mode, and then you don't want to keep going back to the System Analyzer tool. It has all the features that you would have in System Analyzer, but you can just overlay them in the tool, including the real-time overrides. And also, they can be controlled, all the metrics, you can just select 4 at a time, but there's a control panel called Graphics Monitor that we can swap metrics in and out. And within the Graphics Monitor control panel, you can also you can do things that are called triggers. So once we start taking traces and frame captures, we're going to see that with System Analyzer, we can set up triggers so that if a metric goes above or below a certain value, you can trigger automatically a trace or a frame capture. So with this tool, that's how we can just like run through our game, change the different quality settings, look at the different point of views, and just see where we want to focus our efforts on. In the case study that we're going to be talking about, one thing that caught our attention was that one of the things that we wanted to look at was this view where you can look out to the horizon. There's a lot of rendering going on, and also particularly, and we're going to see why in a few, when the HUD is displayed. So now that we have a scene that we're interested in, it's also very important that we can create some sort of reproducible scenario to the best of our abilities. This may be pretty obvious to some people, but if you can't gauge your before and after situation, it can be hard to assess what optimization gains you're getting once you're doing performance profiling. Now that we have that reproducible scenario, we want to gain deeper insight. We want to know if we're CPU or GPU bound. And for this, we're going to use the graphics trace analyzer tool. So before we got into that, I'm going to talk about it a little bit because we just redesigned it last release. And we're really happy with it because we basically redid the UI and the collection mechanism in a way that we can collect much more data. We have a ring buffer mechanism so that if you start capturing after you find an anomaly, the capture will still contain whatever you were looking for. And it also collects various data. If you're familiar with tools like GPU view, we can collect the same ETW events, but we can correlate with some of the things that we can capture with our profiling layers, like the graphics APIs, the debug markers, so you can get a better sense of where you are in your scene when you're looking at the timeline. So graphics trace analyzer can be quite overwhelming. There's a lot of data in it. Like when it collects the system-wide data, so it may be overwhelming for some people. So I figured that we could just keep it on message and just talk about the data that's going to give us the outcome that we expect, which is we want to know if we're CPU or GPU bound, right? So among the data displayed in Trace Analyzer, one of the most critical pieces of the puzzle is the graphics driver and hardware queues. These queues hold all the commands that are required to render to the GPU. And this is crucial to understand if we're CPU or GPU bound. And to understand this, I did a little drawing right here of a percent call and how it traverses through the queue. Each graphics API call produces commands that get put into command buffers, which is what gets submitted to be displayed in the GPU. And it will be placed first on this app-specific queue that it eventually gets to the hardware and then to the GPU. So in this case, we can see that the queue is filled pretty much the whole time. There's no idle time. You just keep submitting commands. And this is a really good way of testing that we're GPU bound. As opposed to not being GPU bound, you can see that not only the queue is smaller, but we have some visible gaps between the queues, which means that the GPU is starving for data. And I want to be careful there because I didn't want to say that if I'm not GPU bound, that I'm necessarily CPU bound, because really there's like that hidden third option of being vsync bound, which if we were going through the workflow, we may not get to that point, but just for completeness, I wanted to talk about it. What would that mean? That would mean that neither CPU or GPU are busy enough, and then they're both basically just waiting for another surface to present. That's something that you can check out in the Trace Analyzer UI when you enable vsync events. And in this case, you're going to see that, for example, those percent calls that you can see down there, even though they look like very long events, the little green bar on top of it, it's the actual thread activity. So you can see that it only was active for a little bit, and then it was just basically just idle until it could continue, and then so on in the subsequent frames. So with that information, we can see just by looking at the data, if we have a consistent stream in the queue, then in the GPU queue, then we're GPU bound. If not, then depending on our frame time and the vsync markers, we will know if we're vsync bound or not. Although, like I said, in this case, I don't think that's going to be necessarily relevant. And then if you see consistent gaps in the GPU queue, then you're CPU bound. And otherwise, it's a combination. And for that, we're going to be talking about one of the new features that are going to help us spot some of these intermittent issues. So before we move on, I wanted to show another thing that Trace Analyzer will show you that is also really helpful. Trace Analyzer could help you figure out if two apps are competing for the GPU resource, and that's also critical if you're doing some performance analysis. You don't want one process to hog the GPU. In this case, I synthetically grabbed two applications and just ran them, and you can see that both of them are submitting events to the queue, and you can see the hardware resource is basically allocating and scheduling time for both. So at this point is where our paths diverge based on our findings, right? And then we pick our path, or more than anything, the path gets picked for us. So GPA, it's primarily a graphics profiling tool. But that said, Trace Analyzer, it is packed with some features that can help us identify CPU side bottlenecks. So before we need to result into like heavyweight tools. So what I want to do now is I want to go through some of these instrumentation opportunities that we have and what gains we could have depending on which instrumentation library we use. So we have three main alternatives for instrumentation in the graphics trace analyzer. We have ITT, which is the instrumentation that you would do for VTune, and then if you do it for VTune, it will show up in GPA. So the benefit there is that you can see it in both. ETW, it's the events tracing for Windows. So again, if you're familiar with tools like GPU View, you can just instrument ETW events and they will show up. Or you can always resort to the good old graphics API debug markers from the flavor of API that you're using, or the PIX markers. In engines like Unity, you can do development builds, and they will do ETW, and they will do the PIX debug regions. And in Unreal, you can enable ITT, and there's documentation in the Intel Developer Zone on how to do that. So another cool feature about the Trace Analyzer is that it has a built-in hotspot analysis, I guess, from the selected region. You can select a region, and it will give you the inclusive and exclusive times. You can see all the occurrences and hover over them, see which ones are your hottest regions. So now that we're done with CPU-bound scenarios, we're going to be looking at GPU-bound. So our goal here is to identify optimization opportunities that can bring the biggest return of investment with the least amount of knowledge of the underlying hardware. And then for these, we're going to be using the graphics frame analyzer, and particularly the hotspot analysis to do most of the legwork for us and like leave all the smarts to the tool itself. So I'm just going to do a little overview of the last tool that we're going to be talking about today. So graphics frame analyzer is our debug and profiling tool. It can capture frames and gather all the data that you would need to present that frame. That means all the APIs, textures, buffers, shaders, et cetera, et cetera. And it really has like a bunch of features that I wouldn't be able to go through here. So I'm just going to keep the introduction brief, and I'm just going to go through the features that are going to help us advance in our profiling workflow. But the one thing that I do want to note is that I'm really excited that in this latest release, we actually released a multi-frame capture technical preview. And what this means is that we can now capture frames through the lifetime of the application. And this is really exciting because like there's a lot of problems that are very difficult to characterize with single frame capture mode, like debugging intermittent glitches, or just multi-frame algorithms that have like a shadow map that just gets updated every other frame. So that it's inherently hard to do in a single frame capture mode because you rely on log to actually catch the frame that you're interested in. But in the case of stream capture, what you can see here is that you get the full representation of the capture of all the frames. And then if you want to focus on one frame, like in this case, the one that has the highest duration, you can just go open. And then that will play back the stream up to that point. And then it will send you back to the frame analyzer that you're already familiar with. We also added the ability to do keyframing or restore points so that you don't need to play back from the beginning, so you can insert these keyframes throughout your capture. But either way, if you do single frame capture mode or the stream mode, they will both end up landing you in the frame analyzer view. And then just to recap, once we get to this view, there's two things that we want to know. We want to know what are our most expensive joggles, and then we want to know why they're that expensive, right? So to find the most expensive joggles, it's actually pretty straightforward. In Frame Analyzer, we have a bar at the top where it shows all of the events that had any GPU work associated with it. This includes like not only draw calls, but also like dispatches, clears, copy calls, et cetera, et cetera. And in Frame Analyzer, we allow the users to control the scaling of the X and the Y axis of this graph. And a subset of the metrics is shown there, but like the list is pretty large. And one of the ones that is really easy to just like bring back to the team and they don't need to know a lot about it is just like GPU duration. If you put it in the X and the Y axis, it will accentuate which are the most expensive joggles. So you're going to see the wider and the most and the tallest joggles are going to be the ones that are going to be more prominent. And subsequently, like the ones that have the most impact in the frame time. So this here is what I tend to call like a bottom-up approach. In my opinion, it's kind of like when you get a task as an engineer and just want to dive into like just start coding it without like taking a step back and just like understanding what the problem is and just trying to take it one step at a time. I tend to prefer, and we're going to be using this in the case study, this top-down approach. And it's particularly useful when you have debug regions. And then you can see the impact of things, but no more at the region level and not at the joggle level. You can still drill all the way down to the joggles, and it's what I keep calling like just like peeling the onion. But at this point, you can see once you enable the debug regions, you can just collapse all of the elements in the API logs list, and then you can see everything per pass. So once we identify the most expensive joggles, now we want to know why they're expensive. So that's where the hotspot analysis mode comes into play. This is a pretty cool feature that when you click on a joggle, it will calculate some metrics, and it's going to tell you, OK, this is the 3D graphics pipeline, and then this is color-coded by which one is your biggest bottleneck. It will also show the metrics that made us infer that that's what it is, and also a little recommendation of like what can you do to resolve this particular problem. And I think this is really cool because it's not, at this point, we didn't need any special knowledge about the underlying hardware up to this point. And then here's where we can just take it a little bit step further as performance engineers, where we can create like these little recipes of like, OK, if you bump into that, it's probably because of this one thing. And I'm going to be given an example of a little recipe that we can do based on the geometry transformation. So if you're geometry transformation bound, your bottleneck is the geometry transformation. And then in my little recipe, all I'm doing is like, OK, what kind of things should I be looking out for? And what kind of things can I do to mitigate the problem? OK, so if you're geometry transformation, then you may want to look out for dense geometry rendered to a small area, which could benefit from like more aggressive LODs or decimation of the mesh. What I've been calling icebergs, which is 5% of it is in the view, and then 95% is out of the view. So maybe it could benefit from slicing the level or whatever geometry a little more efficiently. Or what I'm calling strugglers, which is completely out of the view. You may need to debug your calling mechanism or figure out why that was even sent into the rendering. So once I have this little recipe, I also have like another cool little use of the bar graph. The X and the Y axis can be scaled, like I said, to a bunch of different features, a bunch of different metrics. And one cool way to validate this geometry transformation bound is that if we set the X-axis to pixels rendered and the Y-axis to primitive count, then we can see that if the thinner the bar, that means that we rendered to the less amount of pixels, and then the higher the bar, there was a high primitive count. So tall skinny bars are big objects that render to a small amount of pixels. And in this way, like we see here, we can figure out some of these things. Like in left to right, we get like an iceberg, so just a little bit of it was in the scene, but then the rest wasn't. Then we get a straggler right there that just is not on the scene at all. Or like a combination of things that you can, it's very dense geometry, and there's an iceberg too. But at this point, there's still a problem that now that we remove the dimensionality of time because we don't have GPU duration in the X and the Y axis, even though we spotted all these things, which, by the way, you can see that they correlate, most of them correlate to the geometry transformation as we would expect. Since we remove the dimensionality of time, not all of these may be worth pursuing because they may just take a small amount of time that it's still not worth putting the investment on fixing it. So one of the other features that I wanted to bring up that we just released in R1 is that we now have Excel-like type plugins. So then we can grab the API log, and then we can just type in, OK, just give me the stuff that is GPU duration greater than 200 microseconds. And that way, like, the graph is just going to filter the data. The API log will also filter the data with what you need. But more than anything, like that function metric, that is a Python plugin that we preloaded into the tool. But we are also exposing the functionality so that you can basically create your own thing, and you can create your own set of metrics. You can do and or operations, like if GPU duration is greater than this, and pixel count, it's this other thing, then just show me those values. So it's pretty cool, and it's pretty powerful. So with this workflow, I believe that we can, once we reach to the point where we find these hotspots and then we can create these recipes, I think that we can teach our team like how to identify the scenes and then figure out, just by looking at the trace data without focusing on like all of the other things that they may not care about, how to figure out if you're CPU or GPU bound. And then if you're CPU bound, the opportunities that we have for instrumentation. And again, if you're using a third-party game engine, the instrumentation may already be there. And in the GPU bound scenario, it's just like, how can you quickly, without knowing a lot about it, how can you find the most expensive draw calls, and then how can you figure out where in the bottleneck you'll be? So in our final section, I think what we'll do is like we're going to exemplify this by bringing it back around to the original message of scaling graphics performance effectively and therefore efficiently. So the Unity 3D Game Kit, for whoever's not familiar with it, again, it's a tutorial project from the asset store. You can download it. It has a bunch of levels already in it, and like music, loading screens, menus, and everything. And it already comes with 3 quality settings: performance, balance, and fantastic. You can see here that I just took a screenshot of the performance and the fantastic mode. You can see that there's a drastic visual difference. So the goal was to, how can we bridge the gap between the performance and the fantastic mode so that we can keep the performance FPS with more of the fantastic visual quality? And also the goal for this endeavor was also like, we want to keep it high level. We only want to do optimizations that could have been caught or resolved by our team without recurring to perhaps like a perf engineer to optimize a shader or an algorithm, without also modifying a lot of the content and not modifying the demo drastically. One second. So just sitting back and understanding like what the problem is here, like the first thing that comes to mind is like, okay, what makes fantastic mode looks much better than the performance mode? If we can understand this, we can prioritize our trade-offs once we start like bringing stuff back in. So it's really important just to set your visual quality goals and your performance goals. The performance goal, we already said it, it's at 30 FPS, that's what we want to achieve. And then what are our visual quality goals? So at least in my perspective, there's 3 things that make this very different. One of them, it's the obvious, the draw distance was heavily diminished. The water reflections were also taken out, and the shadows, which just give an overall deepness of the scene. So a little spoiler, this is the outcome of it. It doesn't look exactly like the other one, but it's definitely better than what we can see in the performance mode, and it performs equally good. So how did we get there? So once you have something that is already done and you already have kind of like the min and the max, it's really just a tug of war, right? You're just trying to shave yourself some space, and then you just start bringing things back in, and then just keep doing that until you achieve both your visual quality and performance goals. In cases like this where when a workload is new or the engine is new, I tend to like to just spend some time like understanding how rendering happens. And I skipped a lot of the benefits of using Frame Analyzer, not only for profiling, but also for debugging. This is a really good way of just like understanding your workload. You can just like start clicking on the different draw calls, see how the frame got constructed. And that gives you a better and more like a fuller holistic picture of the frame. So again, collapsing all the regions, we can just start peeling the onion, like I was saying before. And then once we do this, and we said that our frame budget is 30 FPS, we started to see some stuff that were a little fishy. So the first one was this camera is rendering the skybox, and it's taking 3 milliseconds, which is roughly 10% of our frame. And this looked excessive, right? We need to investigate it, because why would the skybox rendering, which is just like a couple draw calls, is just the background, and then there's the clouds themselves, why is it taking 10% of my frame? So debugging it a little further, it turns out that the camera is said to be deferred. So there was a lot of, the draw calls themselves that drew the background were actually pretty small. Just the setup of creating a deferred render target, it was pretty big. So all we had to do is go back to Unity, change it to a forward rendering camera, and bam, we got to a good start. From 10% of the frame, we went down to 2.4% of the frame. So we're making ourselves some room. Let's keep peeling the onion. So we continue traversing the regions. Everything looked normal. I mean, the G-buffer was taking about like, I guess like 6 milliseconds, but we didn't want to touch the content itself a lot. So we just moved on from that. But like the next thing that came to mind was we noticed that the reflections were taking 4.8 milliseconds, which is 14.5% of our frame. And again, this is, first we need to understand why is it taking so much, what is this reflections path, and if it's worth keeping as it is. So once we expanded and looked at the resources, we see that it's creating 32 reflection probes. This is performance mode after all. I do want reflections, but do I need the most accurate reflections? I don't know. Let's see if we can get by with less amount of reflection probes. So we moved 32 to 3 reflection probes, and that brought it down to 6.4% of the frame budget. So we thought that that would still give us some reflections. They're not going to be as accurate, but they still give us some reflections. But it gave us a little bit more room to bring the things that we really care about, which were our visual quality goals. So moving on, the next thing that kept like bugging us is the fact that you see that there's the UI rendering, and it's taking like about like 8% of the frame, 1.8 milliseconds. And this was particularly troublesome because there's literally, it's highlighted right now in that different color, but it's just two boxes that were rendering UI. Why is it taking so long? So with this, I also didn't touch on the simple fragment shader. With the simple fragment shader, we were able to change the shader to like a trivial shader and see what kind of gains we would get. And we noticed that that would be very beneficial. So we went back to Unity and looked at the shader that it was executing, and it turned out that this blur shader was a little bit expensive. So do I need this blur shader? Would I rather have my other things that I want, which is my water reflections, my shadows, my draw distance? So it's like, okay, first let's assess, let's remove the blur, let's see how much gain we would get. And sure enough, it went down from 1.8 milliseconds to 0.2 milliseconds, just 0.6% of the frame. With this amount of gains, I don't care about that blur. I care about these other things a little better. One thing that I forgot to mention too, like it's the skybox optimization, that is not specific. In this case, we had a compromise, right? Like we changed the visual quality because we just changed from blurred to not blurred, so it changes the look and feel of the game. But in the case of the skybox, that did not change anything visually, which means that that optimization actually will be applied both to the mainstream graphics and to the high-end, to the fantastic mode if it gets applied there too. So that's part of like that symbiotic relationship that I was talking about while optimizing for either one of the types of hardware. So at this point, we had enough room, so it's like, okay, we have a level check. Let's see how we're running to see how many things we can bring back in. We're running at 38 FPS now. Personally, don't usually talk in FPS terms because of the non-linearity of it, but that's what the HUD shows, so we're going to stick to 32 FPS right now. It was time to start adding things back. So what was the thing that we thought that would be the most costly? It's like, okay, let's add the culling distance, because with the culling distance, we're going to start to render a bunch of new things, and we think that's going to be one of the most expensive things, and it's going to give us one of the biggest visual improvements. So sure enough, we brought that back, and then that took us from 38 to 33. We still have a little bit of room, and it already is looking much, much better. So let's just add it all. Let's bring back shadows and water reflections. And we went a little bit over budget, 28 FPS, but we got everything back, and it's looking much, much better. But we don't want to cheat. Our budget is 30 FPS, so what can we do cheaply to stay within budget? So the next thing was like, okay, we don't want to modify the content, so we don't want to modify anything inside the G-buffer, but perhaps we can get by with shrinking down the size of the G-buffer a little bit to, and then still do a full screen pass later so that the UI still looks crisp. So we ended up doing that, and I put a big screenshot here so you can see that there's really not that much of a visual degradation, especially when you consider all the things that we brought in. So we brought that 30 FPS. We brought the waters, the shadows, the draw distance, and then we kept our 30 FPS. We're back within budget. And that's my last slide before the summary. I just wanted to point out that it's really important to scale graphics performance effectively. Hopefully this was helpful for you, and hopefully you can bring this back to your team and just like teach them some of these like quick tips, I guess. Performance awareness is everyone's responsibility. It's not only the performance engineer. I know we tend to suffer the burden of it. You can grab Intel GPA for free. And you can literally try this yourself. Like this demo, it's free. You can download it in the asset store, and you can basically do what I did here and just play around with the tools. So with that, we can go into questions, and then we'll go to the raffle. Clear as mud?